problem 2.3. So problem 2.3. Problem 2.3 says that we're given the initial state, so 1 atmosphere pressure, 1 liter volume, 373 K, and we undergo an isothermal expansion to 2 liters, and then after that we cool it at constant pressure to some volume, and this volume is such that we can then apply an adiabatic compression to restore it back to the original initial state. So we're going to do a closed loop, and these are reversible processes. We're supposed to find this particular volume, and then we're supposed to calculate the work done by the gas. And again, this problem needs and does not give us the heat capacity, so we're going to take the molar constant volume heat capacity to be 1.5 R. And this is page 8. So let's write this out. P1 is equal to 1 ATM. V1 is equal to 1 liter. T1 is equal to 373 K, which means N1 is equal to PV over RT is equal to 1 times 1 over 8.2 times 10 to the minus 2, 10 to the minus 2 times 373 is equal to 3.3 times 10 to the minus 2 mole. And this undergoes isothermal expansion to P2 V2 is equal to doubling it, so 2 liters. T2 isothermal, so it's the same temperature, 373. Sorry, I'm going to zoom out. 373 K, and N is still fixed at 3.3 times 10 to the minus 2, which means that our pressure can now be written nRT over V is equal to 0.5 ATM, substituting in 2 liters, 373, 3.3 times 10 to the minus 2 for N, and in for R, it's 8.2 times 10 to the minus 2. Okay, so we got that. And then this is going to go constant pressure to P3 is equal to 0.5 ATM, constant. V3 is equal to our unknown volume V. T3 is equal to PV over NR is equal to 0.5 times V over 3.3 times 10 to the minus 2 times 8.2 times 10 to the minus 2. T3 is equal to 185 times V. And N3 is still equal to 3.3 times 10 to the minus 2. And this is going to be, well, let's draw it this way. Adiabatic. A-D-I-A. So we got these three states. Okay, well, the good news is we can find the volume because we know that this is an adiabatic system, meaning that P1 V1 to the gamma is equal to P3 E3 to the gamma. Because we have the heat capacity, we have gamma is equal to Cp over Cv is equal to 5 halves R over 3 halves R is equal to 5/3. Or V3 is equal to P1 V1 to the 5/3 divided by P3 raised to the 3/5 is equal to 1 times 1 to the 5/3 divided by 0.5 to the 3/5. E3 is equal to 1.51 liters. So that means this is now 1.51 liters, and that changes the temperature, or determines the temperature. The temperature is now determined to be 280 K. Okay. So that was the first part of the problem. And the next part of the problem is to determine the work for each one of these three transformations. And this is on page 9. The first, from state 1 to state 2, is isothermal. So W1 to W2 is equal to nRT natural log V2 over V1 is equal to 3.3 times 10 to the minus 2 times 8.314 times 373 natural log of 2. W12 is equal to 70 joule. And the second transition is constant pressure. So W23 is equal to P delta V is equal to 0.5 times 1.51 minus 2 times 101. That's joule per atmosphere liter is equal to minus 24.7 joule. Or it's right up here, I guess. And then the next transition is adiabatic. In this adiabatic transition, W31 is equal to the change minus the change in internal energy, U, because we have remember delta U is equal to Q minus W. That by definition is definition is 0, so we get delta Q and that, or delta U, and that can be written in terms of the heat capacity. Integral from 280 to 373 N CV dt is equal to minus 3.3 times 10 to the minus 2 times 3 halves times 8.314, 3 halves R, times delta T, which is 373 minus 280. And here we get W31 is equal to minus 38.3 joule. And we get W is equal to W12 plus W23 plus W31 is equal to joule. W.